Hello, Namaste. Welcome back to the course on Geographic Information System. In the last week, we were looking at how do we look at the spatial analysis part of GIS. So now, when we are looking GIS as a tool or software, the first thing that comes into mind is how do we do the analysis. Okay, having said and done with the theory, the next step is to how do you do an analysis. So in this aspect, this particular week is basically trying to give you a flavor of what are the different types of analysis is done, whether it is spatial analysis, whether it is advanced spatial analysis, or whether it is what are the limitations of GIS data at the end. So this week has been broken down into three parts. First part, I would give you an introduction to what do you mean by remote sensing. Okay, having said this is just an one short introduction to remote sensing, but it is not limited to what I speak. So you would have to, if you have to understand remote sensing, you have to go beyond at least very beyond what I have already taught in this particular set of slides. In the next classes, I would look at next 2 or 3 classes, I would look at what do you mean by spatial analysis, the basic spatial analysis, which already I have spoken about a few of them, but I would go into emphasis with some examples. Next, I would look at advanced spatial analysis with again some examples, and finally I would end this particular week with what are the limitations of having a geographical information system in place. So this would be the entire course of week. So in today's class, let's understand what do you mean by remote sensing. Okay, so in this class I would give you an just sneak peek into what do we understand by basics of remote sensing. What do you mean by a remote sensing? Are you really doing a remote sensing when you are actually looking at me through this particular set of video slides? And when you are looking at this remote sensing, what are those principles that you have to understand when and how they actually interfere into your to form an image is what we have to understand. And finally, I have given a small set of introduction to what do you mean by different resolutions. For example, we were speaking about data. When you are looking at data, it means to say that the data has to be measured in certain form. Now if someone is trying to use the satellite data, okay, so satellite data has different qualities which is called as resolutions. Okay, this is the first and the foremost thing that you have to see in a satellite data. So in order to understand that, I have included what do you mean by a resolution, a spatial resolution or a spectral resolution or radiometric resolution. So this is what would be the flow of today's class. So when we, for example, when you are looking at this particular video lecture, so you are actually sensing it without being in a contact with the person who is teaching it. Yeah. So when you are not in a physical contact, it means you are remotely sensing this particular presentation which I am trying to do, which means I am remotely present and you are trying to analyze or grasp whatever I am trying to inform it to you. That's nothing but remote sensing. So if you want to define a remote sensing, so let me be very specific. It is a science and art of obtaining information. Okay, information is the last part of data analysis in remote sensing, which becomes data for us. Okay, so it is a science and art of obtaining information about an object. It can be an object, it may be your building, it may be any rock type, it may be a soil type, it may be water type, an area, entire city, entire colony, or it may be any of those regions, or a phenomena. It may be your landslide, it may be your earthquake, it may be your forest fire, or it may be your floods. So these are phenomena. So it can be an object, it can be an area or a phenomena through the analysis of data acquired by a device that is not in physical contact. So now if you have a camera here and you are trying to acquire a object, area or a phenomena in your camera, in your mobile phone camera, then it becomes you are remotely sensing an object, area or a phenomena which is under investigation, which you are trying to capture. Okay, for example, when you take a selfie, so what are you trying to do? Basically you are trying to capture yourself as maybe as an object and trying to place it in your a lens that your camera captures. So, it captures certain amount of light. Okay. So, that is nothing but sensing remotely. So, you are not in contact with that particular sensor, right. So, you have a remote sensing object which is nothing but a camera, and you are taking a picture. Similarly, the same concept applies with satellites which are placed somewhere around 800 to 900 kilometers away from the Earth's surface. Okay. So, these sense the Earth's surface in terms of whatever is the display, whatever is the object, area, or a phenomena. Based on your application, you try to see that what kind of information that you need. So, that is what is remote sensing. When you look at remote sensing, you have two types. One is called passive, other one is called active. So, when for example, if there is a sunlight, a source of energy which is not emitted from the satellite, and this hits the Earth's surface, and there are certain amount of reflections that is again captured by the satellite. So, satellite does not have a source of energy, then it is called a passive remote sensing. If satellite has its own source of energy by various means, for example, when you are looking at microwave remote sensing, okay, so you have your own source of energy which hits the Earth's surface, and the certain amount of reflections are then captured by your sensor on board those satellites, then it is called an active remote sensing. So, when you look at this image here passive remote sensing is done using a solar energy, which is 99.99% of the time. Okay. So, here you have a satellite which is sending out its own form of energy which is hitting the Earth's surface, and then it is captured back in the sensors placed on board the satellite. This is called active remote sensing. Okay. So, when you look at remote sensing, you, as I said, you have a passive remote sensing, you have an active remote sensing. But when you look at different sensing system, you have satellite remote sensing, you have an high altitude, low altitude, and a ground level. When I say satellite is at about 800 to 900 kilometer away from the Earth's surface. High altitude systems are placed at least at 20-30 kilometers from the Earth's surface or a bit away, so that it can capture a certain amount of area. Low altitude remote sensing is normally done just above the ground level, which may be about maybe a kilometer or another 2 kilometers away from the Earth's surface. But ground level remote sensing is on the ground. So, you have a sensor that is almost closer to the ground level. So, that is how you do the remote sensing. So, now you have drones which again have the low altitude remote sensors. So, that also drones fall into the aspect of, or UAVs fall into the aspect of low altitude remote sensing. Now, once you have sensed the data, this data is either then transformed into a digital data, which may be in the form of a raster image, or it may be in the form of a numerical data if it is sensed in a certain aspect or a certain phenomena, or it may be in the pictorial data, only the captured image that has been considered, or it may be in the form of a reference data. So, reference data is extremely important when you want to validate remote sensing data. So, you need a reference data. So, it is in the form of a reference data. So, once you have acquired these kinds of data products, okay, the next step is to interpret. So, what I am trying to tell you is how remote sensing progresses, how you have captured the data and how it actually forms information to the user. Okay. So, next thing is interpretation. Once you have captured this data, you have to interpret either in the visual interpretation or in a digital interpretation. Use various algorithms, sophisticated algorithms to do all kind of analysis, whether it is statistical, whether it is numerical. So, you try to use a lot of algorithms, or there are methods where you do visual interpretation, where visually you will say this is a particular part of the Earth's surface which belongs to this category. So, that is the third step, and the fourth step is providing an output to the user. It can be a map, it can be images, it can be numerical reports, it can be technical reports. So, depending on what category of users you are trying to give the information to, it is dependent on such users for their analysis. So, you will give that kind of information. So, now when we look at these two things, you have two types. One is data acquisition, data analysis, and the user. So now data acquisition means you have passive or active sensors, sensing systems which are either passive or active sensors. Then once you have acquired the data, then data products are in certain formats. This is then started to look at by the analysis. Analysis either is done by the sensing agencies. For example, NRSC also has a lot of other agencies like SAC, IRS, etc., which actually do a lot of work on this kind of remotely sensed data. You would have probably seen a lot of work, especially if I have to highlight a work with when there was floods in Uttarakhand and very recent the earthquake, etc. So all of these are actually captured and very nicely analyzed by the agencies itself, and there are users who actually take these data and use them and also produce reports. It may be technical reports, it may be outputs, it may be peer reviewed papers, it may be images, maps, etc. So these are the two parts that we can distinctly say that remote sensing is made of. One is acquisition and the one is analysis. So when you are looking at remote sensing as an complete package, the first thing is you have a source of energy. For example, here I have considered sun as a source of energy. The solar energy hits the earth surface. There may be many things on the earth surface. It may be high rise, it may be low rise, etc. Okay, paved road, bare soil or wet soil, grass, water, forest, okay, so grassland. So all of these, they have their own reflecting ability. Okay, the reflecting ability is very different for each and every surfaces on the earth or objects on the earth surface. So this the amount of reflectance that reaches the satellite is then captured by the sensors on board the satellite. This is what is then converted from an analog form to the digital form and then given to you as a data. It's when the data is sensed by the sensor, it is normally in the analog form. Then you convert it into a digital form, and when I look at the digital form, for example, you would have zoomed into certain images. If you just take a photo of yourself, zoom in as much as possible, so you would look at pixels. So each of these pixels, because it is representing certain amount of reflection, has its own digital number. Okay, so that's the amount of reflectivity that is there. Okay, so it represents a digital number. That is what is captured by the sensors on the satellite. Okay, so that is amount of reflectivity of each and every that is what differentiate every aspect on the earth's surface, whether it's a phenomena, whether it is an object, area, or a phenomena, whatever it is. So that amount of energy that is actually recorded on board a sensor is very different from each of them, and that differentiates everything. Okay, so and the very important aspect that you have to look at here is, the first thing is electromagnetic spectrum. So I hope many of you would have learned what do you mean by an electromagnetic spectrum, but electrical field and magnetical field are propagating at 90 degrees is nothing but an electromagnetic spectrum. Okay, so now when you let's say that this is the wave that is actually propagating. I have just taken either electrical or a magnetic field. The distance between a successive crest or a distance between a successive trough, okay, either this or this is called as a wavelength. Okay, and number of cycles passing, for example, this is one cycle, okay, passing at a particular point of time is nothing but your frequency. Okay, so when you look at this can be explained very clearly by the laws of energy. The same laws of energy is applicable in terms of remote sensing. When there is longer wavelength, you have lower frequency. When you have lower frequency, you have lower energy. When you have shorter wavelength, you have higher frequency and higher energy. Let me explain it to you by the this particular equation. If you have looked at energy of quantum, it is E is equal to h nu, which you can see here. Okay, when you look at it, it is E is equal to h nu. Okay. When this particular aspect is considered, okay, frequency is c by lambda, okay, where c is nothing but your constant or the speed of light and lambda is your wavelength. So, which means that E is equal to h c by lambda, okay, or E is equal to h f, right. So, now energy is directly proportional to the frequency. So, lower energy, lower frequency. Energy is inversely proportional to the wavelength. So, lower energy, longer wavelength, higher energy, shorter wavelength, okay. And h is a Planck's constant, which is 6.626 into 10 power minus 34 joule second, okay. So, this is the first principle that you have to understand in terms of understanding remote sensing, okay. So, energy of a quantum or quanta is measured as E is equal to hf or h nu. So, nu is nothing or f is inversely proportional to the wavelength, that is h is equal to c by lambda. So, f is equal to c by lambda. So, E is equal to h c by lambda. So, when you look at this equation, frequency is directly proportional to your energy, and when you look at your wavelength, it is inversely proportional to the energy. So, how does it affect your remote sensing? If you ask me how does it affect, for example, if you look at your frequency range, if you go back to your electromagnetic energy distribution, so if you have the lower wavelength, it will have higher energy, which means your visible spectrum or even below that will have higher amount of energy, whereas the ones which have higher wavelength will have lower energy, or longer wavelength will have lower energy. So, it is easy to capture more amount of information when it is of in a longer wavelength, in a shorter wavelength, but with high energy and high frequency. So, this is how it is implicated in your remote sensing, okay. So, when you look at the entire electromagnetic spectrum, that is what I was trying to explain. If you look at this, the radio waves is in this region, okay. Then you have certain part of the microwaves where you have radars that actually work, okay. Then you have a certain part of energy which is actually the visible energy, okay, which is here 0.4 micrometer to 0.75 micrometer, okay. So, when you look at this part of the energy, you can see that this is in the lower end of the spectrum, okay, which means that it is in the shorter wavelength region, okay. Once you have shorter wavelength region, it means to say that it has higher frequency. Once it has higher frequency, it means to say it has higher energy, okay. So, that is what I intend to explain here. Then if someone asks you what is the wavelength of region of visible region, you should be able to say it is 0.4 micrometer to 0.75 micrometer, okay. So, that is very important when you are actually explaining the electromagnetic spectrum. Then you have ultraviolet, then you have soft X-rays, and this is also called as infrared, where this is the short infrared, mid infrared and far infrared, and then you have thermal infrared, okay, until 10 to the power of until 10 to the power of 15. Then you will have hard X-rays and gamma rays, okay. So, that is about the electromagnetic spectrum, okay. To give you more understanding about it, if you look at the wavelength here, this is where the visible region is there, and if you see the wavelength is shorter. When the wavelength is shorter, it has higher energy, the energy is very high. As the wavelength increases, the energy decreases. So, when you look at the sun's wavelength is somewhere here, okay. So, energy is much lesser. When you look at the earth's surface, you can see it here. The same thing is very much reciprocative in terms of transmission, okay. So, I'll speak about this when I speak about other two laws, but why I am very particular about this is to just understand how the energy and wavelength are related. And when we come to the next law is the Stephen-Boltzmann law, which states that it is W equal to sigma T to the power of 4, okay, where this is a constant which is Stephen-Boltzmann constant, which is 5.67 approximate, it is 5.6692, so it is approximated to 5.67 multiplied by 10 power minus 8 watt per meter square per degree Kelvin, per Kelvin to the power of 4, okay. So if you look at this, okay, this particular thing, this is Stephen-Boltzmann's law, then you have total radiant emittance, which is watt per meter square, and T is the absolute temperature, okay, of the emitting material, okay. What are the material that is emitting? That is nothing but T. So now when you look at this, if the emittance from the material, okay, the total radiant, it means radiative, the one that is coming out after absorption, emittance is proportional to the fourth power of the temperature. So higher the temperature, okay, higher the emittance, lower the temperature, lower is the emittance, okay. This is one. The next law that we have to understand is Wien's displacement law, which states that lambda is inversely proportional to the temperature, which means that wavelength is inversely proportional to the temperature. Now if the wavelength is higher, temperature is lower, if wavelength is lower, then the temperature is higher. So which means to say that lower wavelengths here have higher temperatures and higher radiant emittance, lower wavelength will have higher temperature and higher emittance, whereas higher wavelength will have lower temperature and higher radiant emittance. So this, both of these law has to be understood in concurrence, so that you understand how this is related to your earth surface, okay. So I hope you guys have understood this. Let me go to this example to explain you much more. So what did we say? W is proportional to the fourth power of the temperature and lambda is A by T, correct, which means higher the wavelength, lower is the temperature. If the temperature is lower, then your emittance or the radiant emittance is lower. Now I have plotted a curve which is on spectral radiant emittance, okay, versus the wavelength, and when you see it, this is where is your exactly the visible wavelength, okay, and where you look at the visible wavelength, the temperature is of a black body. When I say black body, it is a hypothetical body where which has complete absorption and complete emittance. So when you look at the temperature of the black body is the highest, and that is where is exactly your visible region located, which means that it is easy for anyone to capture in the visible region. That is why human is able to look at visible region by his own eyes. So that is why you can easily connect with RGB. Any of your colors are with the primary colors, which is red, green and blue, okay. So when you look at this, this is blue, green and somewhere here is red, okay. In the electromagnetic spectrum, if you look at blue can be somewhere around 0.4 to 0.5, where green is 0.53 to 0.63, okay, and your red is somewhere 0.64 to 0.75, okay. So if you see, it is the maximum, the black body radiation is at the sun temperature is maximum, that is 6000 degree Kelvin, and that is exactly where is falling on the visible region. And when you look at this Earth's temperature, if you look at Earth's temperature, black body radiation is about 300 degree Kelvin, where if you see the wavelength is much lower, and hence that amount of emittance is much lower. So, if you look at it, anything sensing here may have a lot of loss, because most of the energy would have been absorbed and the very less amount of energy is emitted back. Okay. So, that is the example that I am trying to tell you, that how it is different from each other. Okay. To explain it to you more about how this works, first you have the solar radiation. Okay. Let us say this is solar radiation that is coming into the earth surface. So, let us say this is sun. Okay. Now, once you have the solar radiation, you have a thick layer of atmosphere here, correct. There you have a phenomena called as scattering and absorption. Due to either scattering or absorption, or due to both, there will be a certain loss of energy. Okay. Now, with this loss, certain amount of energy reaches the earth surface. Now, in that, let us say there is certain amount x loss. Okay. Now, with this, some amount of energy is reflected, some amount of energy is absorbed by the earth surface or object, etc. Some amount of energy is reflected, right. So, this energy that is reflected is again transmitted in the atmosphere. Again you have atmospheric interference and you have certain loss. This, after this, the amount, so you have three kinds of losses where certain amount of energy is absorbed. Here certain amount of energy is either scattered or absorbed in the atmosphere, then again while going back you have certain amount of energy that is scattered or atmosphere. The amount of energy, that is reflected energy, that is left after the atmospheric transmittance, then that is the energy that reaches the satellite, that is recorded onto the satellite. That is what you would get as an image once it is converted from analog to digital signal. Okay. So, this is exactly the process of how remote sensing is done using a satellite. Okay. So, this just to give you a flavor. There are more things that you have to understand if you have to understand this specific object aspect in much better way. Okay. So, this is just an overview of how it actually works. The other thing that we look at when we are understanding remote sensing is nothing but a spectral reflectance curve. When I say a spectral reflectance curve, it is the curve where y axis is the reflectance, that is the amount of energy that is reflected back from that particular object after all this loss is there, the amount of energy that is captured, versus the wavelength. Okay. For example, if we consider vegetation. So, if we look at vegetation in this, let us say this is this is a blue band, this is a green band, and this is the red band. Okay, red band is somewhere till here. Okay, not till here. So, if this is the red band, now you have green and red. So, now when you look at this blue, it has a very less reflectivity. In the green band, it has a little amount of reflectivity. In the red band, it comes down. The reflectance is only 10% or even less. Okay. Then in the near infrared zone, it has very high reflectance. Okay, which means to say that vegetation has the characteristically reflects in the near infrared band. Now, if you use your eyes to measure the reflectance of vegetation, okay, your naked eyes will not be able to distinguish between two vegetation, because you would not be able to sense in the near infrared band. Whereas, when you sense in a sensor which actually captures the reflectance, so you could easily distinguish between two different plants or two different characteristics of a plant where the reflectance in the near infrared band. So, that is very high in vegetation, and when you go ahead, it has 3 dips here and in another dip in 2.7. So, this is called water absorption bands. Okay, this is exactly for studies of vegetation, the water content, etc., and its relationship. Okay. So, this is the characteristics of your vegetation. For example, if someone wants to understand what is the amount of vegetation versus non-vegetation, he or she would actually compare two things. One is you have very high reflectance in near infrared band and have a very low reflectance in red band. So, that is how people calculate a index called NDVI, which is NIR minus R by NIR plus R. Okay. So, which gives you the normalized values of vegetative index. The positive values are indicating the vegetation. Higher the positive value is the thicker the vegetation, lower the values is the sparse vegetations, and if you look at the value closer to 0 is actually representing water, and the reflections that are much in the negative value is actually representing soil, okay, or non-vegetative characteristics. So, that is how people that is how you can understand the difference in the characteristics on the earth surface. One example is what I gave it as NDVI. And when similarly, if you add the aspects of water, water has highest reflectance in the green band and lower reflectance in the red band and complete absorption in all other bands. So, it means to say that if you use a near infrared band, water is completely absorbing and hence it should be looking black. Okay. So, if someone wants to just extract water, he or she would just take a near infrared band, and wherever it is 0 or a certain values, it may not be exactly 0, because there may be certain characteristics of that particular water body which may be emitting certain amount of energy. It may be there may be plants, there may be etc. So, you look at exactly and just see that if you can with that amount of digital numbers, it can be easily separated as water and non-water. Okay, that is called as thresholding. Okay. So, this is one aspect of water, and you have this is the reflectance curve of soil. So, based on the same reflectance curve, you can look at the various properties of the soil. It too has water absorption bands here, which is actually representing at 1.4, 1.9 and 2.7. So, amount of water present in the soil can be easily measured at this particular point, and there are huge number of studies in understanding this particular reflectance curves. So, having understood all of these are very basics of remote sensing. The very important aspect that you have to understand is the spectral reflectance curve. If you have understood that, the very basics of the remote sensing is actually understood by you. Okay. If someone has an access to a spectroradiometer, please look at how you can measure different plants, different soil. So, you will understand how this particular spectral reflectance curve versus wavelength is actually computed. Once we have understood that, let us go to the satellite. Now, as I said, satellites, what we are trying to understand here is the polar satellites. Basically, I would be very much concerned about the passive remote sensing. And when you are looking at any of these satellite data, the first thing that you have to see is the metadata. The second thing that you have to always look at is the different kinds of resolution. If you have the data already with you, if you do not have a data already with you, then the first thing that before even considering any data, you should understand what kind of resolutions that you need. Okay. For example, if someone is looking at how the growth of a city is happening or city pattern you are trying to understand, there is no need to actually buy a very very costly high spatial resolution data. Okay. But if someone wants to really see the building wise or the road wise information of a particular city, then you need to have a very high spatial resolution data. So, first understand what is the application of your data. Okay. Without understanding the application of your data, it is impossible for us to understand why that particular data has been considered, or it will be really not an real aspect of working on the data. So, when you want to buy a data first thing or download a data, the first four things that you have to understand is spectral, spatial, radiometric and temporal. though temporal is completely fixed when the sensors are actually placed on the satellite, but the other three things are extremely important for your analysis. The first thing is spectral resolution, the second one is the spatial resolution, and third one is the radiometric resolution. So these three have to be looked at even before you buy a satellite or buy a satellite data or download any satellite data. Okay, without understanding these these aspects of any satellite data, it would be really a problematic issue if you are trying to download any data. Okay, so let's go by each one of them. The first thing is spectral resolution. When I say spectral, how far, when we have looked at the EMR spectrum, okay, if we try to draw this, okay, let us say these are the wavelength point, this is the wavelength, okay, 0.5, 0.6, 0.7, okay, then you have 1.2, 1.4, 1.6, then 1.8 and so on. Okay. Now, if I try to use, okay, let us say our satellite sensors are able to categorize each of these electromagnetic spectrum into different bands. For example, there is one satellite which can capture this spectral band, this spectral band, this spectral band, and this spectral band, and this spectral band. This is the spectral resolution of that particular satellite, which means it has one band, 2, 3, 4, 5, which means to say that a satellite has sensors which can capture in these different bands. So this is nothing but a spectral resolutions. Okay, it is extremely important in terms of what kind of resolution. For example, if you are trying to understand vegetation, you need to, as I said, you have some very high reflections in the near infrared band and then have a low reflections in the red band. So you will obviously consider a satellite which has all of these bands. If you are using it for a variety of applications, you would probably look at those applications and look at what kind of, how many number of bands you need. If a satellite is then capturing this as entire electromagnetic spectrum in a single sensor, okay, then it is called a panchromatic band, okay, or a pan band. Okay, this means to say that this entire spectrum is then captured. It may be this entire spectrum, it may be this whatever the spectrum it captures. So it when it captures, then it is actually said as panchromatic image. Okay, specifically normally it is done until here. So it once it captures this, then it is called a panchromatic band, and this panchromatic band has only one band or one specific image. But these, when I said there are different sensors which is capturing at different regions, it means to say that these are different images. Okay, so different multi images. So it is multispectral, it is called MSS image, okay, or multispectral sensors. So you have multispectra of sensing. Okay, so when you look at this, you have collection of image. If you are actually collecting everything in a single strip, then it is called a panchromatic. This only one particular sensor or set of sensors capture the entire region. Okay, now the very interesting part is that if instead of this, if I capture like this, very narrow spectrum, then it is called as hyperspectral sensing. Okay, so if the entire spectra is captured by a single sensor and single band, then it is called panchromatic. If the entire spectrum is captured by multiple sensors, it is called multispectral sensors and or multispectral images. And if it is captured by if you narrow spectrum of band and you have a huge amount of bands that it has been captured, then it is called hyperspectral sensors. Okay, this is about the spectral resolution. To just give you an example of what do you mean by spectral resolution, if this entire, I have just taken a visible wavelength. So, if the visible wavelength from 0.4 to 0.7 micrometer, this is one of the examples from Canadian Space Research Center, which explains how the spectral resolution is there. So, when you, if you look at the entire from 0.4 to 0.7 is sensed by a single sensor, and you have an output as a image, as a single image, then it is called a single image, or its a spectral resolution is 1. If the same energy spectrum, this is 1, this is 2, this is 3, is broken into 3 different sensors, and each sensor is capturing at 3 different wavelengths, then it is, its spectral resolution is 3. Now it is sensing at say different 6 different, it has broken the same thing into 6 different parts. So, 6 different sensors are capturing it. So, which means to say that this spectral resolution is 6. Okay. Next concept is the spatial resolution, and when you look at spatial resolution, it is the finest area that you can look at in that particular image. Okay. Or it can be defined as how much a pixel can capture in its own place. For example, if I say it is a 30 meter pixel, the spatial resolution is 30 meter. So, it says that a pixel carries 30 meter by 30 meter information in that particular pixel. If I say 1 meter, then it says a pixel can carry 1 meter by 1 meter information. Okay. So, just to give you an example of how what are different. So, the first, this is the original image, which is 1 meter resolution. So, you can see very fine details of that of a set of buildings, and this is called a very high resolution image. Okay. You have submeter also, now you get images at 25 centimeter, 60 centimeter, 90 centimeter, etc. So, this is one of those very high resolution data. Indian satellites have very good capability of capturing at now at even the submeter levels. So, you can find out, you can contact National Remote Sensing Center for any of these data products, which you can always acquire. Then the same image is then resampled to 2 meter, and the same image is resampled to 30 meter. Okay. So, which means this particular pixel here and the pixel here. Okay. This pixel is representing 1 meter by 1 meter, this pixel is representing 30 meter by 30 meter, which means it is more, this is a coarse resolution data, 30 meter pixel is a coarse resolution data, whereas this is a 1 meter is a very fine resolution data or a very high resolution data. Okay. So, this is about resolutions, and if you want to look at it pictorially, this is 30 meter by 30 meter. If a house is pictured, this is the house. Okay. If this is pictured as 30 meter by 30 meter in 1 pixel, let us say. The same house, if it is taken into 5 meter by 5 meter, you can see the number of pixels that is it is being denoted into. So, maybe one part of the house, your dining room or your kitchen, maybe in a pixel. Okay. The same house, if it is captured in a 1 meter resolution sensors, then maybe even a very small part of a kitchen, okay, maybe your kitchen sink is actually coming in a single pixel. Okay. So, that is what is the difference. Okay. Just to give you an representative features of how the resolution is important. So, spatial resolution is about how much area it actually covers in a pixel. Spectral resolution is how the sensors can actually capture the electromagnetic spectrum into number of bands, and the third one is the radiometric resolution. So, when you look at radiometric resolutions, it is about how many radiometers that this has. For example, if your picture can or your sensor can picturize that particular part of the earth's surface in only 0 and 1, okay, then it is called a 1 bit resolution, or radiometric resolution is 1. If it can capture between black and white, see this is black and white, always your image that is captured in different sensors in the gray levels. So, if the gray levels range from black to white, so if number of gray levels is 0 to 3, that is 0, 1, 2, 3, then it is called a 2 bit radiometric resolution is 2. If your gray levels is represented by 0, 1, 2, 3, 4 until 255, which means it has 256 levels, then it is called an radiometric resolution is 8, okay. And if you have 10 bit, then if the ranges will be from 1 to 1023. I was speaking about digital number. So when I say radiometric resolution, number of gray levels that can be represented, it is same as your, it is equivalent to your digital number. Higher the digital number will have higher radiometric resolution, lower digital number will have lower radiometric resolution details. For example, if your image, if you have bought a, if you have actually acquired a Landsat data, Landsat data is a 8-bit data, which means its radiometric resolution is 8 and its values lies between 0 to 255. 0 is completely black. If you take an infrared image, 0 is representing a water body, so it is completely black, and whereas 255 would be representing the highest reflected object from the earth surface. So just to give you an example of 8-bit and 2-bit, if you look at it here, 8-bit you can, it is easier for you to understand different aspects on the earth surface, whereas in your 2-bit it is very difficult for you to understand different objects on the earth surface, because it can distinguish only 4 different colors from in gray combinations, whereas in 8-bit it can actually look at 8 different gray combinations at different instant of time. That is why higher the radiometric resolution, better is the quality of your data, okay. Now the last thing is the temporal resolution. When you look at temporal resolution, it is often how often that particular satellite can capture, or a sensor can capture the same part of the earth's surface. For example, Landsat has 16 days, ICONOS has 1.5 days for a multispectral sensor and 2.5 days for a panchromatic sensor. MODIS on an average has a 16-day repeat, but 1 to 2 days coverage, okay. These are different sensors, very interesting sensors, satellites and sensors. You can look at all of these, and AVHRR is one of them, where 9-day repeat cycle, and you have GEOS, which is about 30 minutes. So this is about temporal resolution. It is the last kind of resolution that is actually to be understood. So to summarize this particular class, we have looked at what you mean by and what do you understand by electromagnetic spectrum. First, we looked at what is remote sensing, then different parts of electromagnetic spectrum, then laws. We started with energy of a quanta, E is equal to h nu. Then we looked at Wien's displacement law. So once we Stefan's Boltzmann law and Wien's displacement law. So once we have understood this, when we looked at a spectral reflectance curve, okay. So it is a reflectance versus the wavelength. So whenever you are looking at any aspect of the earth's surface, or when you are trying to capture it, first thing is look at the reflectance curve. Then is the resolutions of the, we ended this particular class by resolutions of satellites, where we are looking at what are different resolutions that you have to consider when you are considering the satellite data products. So this is just about a small part of remote sensing. In the next class, we would go back to GIS. We would look at what are the basic spatial analysis, very advanced spatial analysis in the rest of 4 classes of this particular week. Thank you very much. See you in the next class.